To remain useful, an enterprise AI system requires a constant stream of new data. But once the initial training run concludes, the neural network suffers from structural amnesia. It can process new prompts, but it cannot permanently retain new information without undergoing another massive cycle of intense processing. The traditional method for updating an AI's knowledge base is continual fine-tuning. This involves retraining the model on new data through a process called backpropagation, mathematically adjusting the strength of billions of internal connections to minimize error. This introduces a mathematical flaw known as catastrophic forgetting. Because neural network weights are highly interconnected, adjusting them via backpropagation to memorize new data inherently overwrites the exact parameter combinations that governed the model's previously learned foundational reasoning. It loses the old logic to accommodate the new fact. The energy cost of this constant retraining is scaling at an unsustainable rate. Since 2012, state-of-the-art training compute requirements have doubled approximately every 3.4 months, outpacing Moore's law and driving a massive spike in data center power consumption. This exponential demand for compute is now colliding directly with the hard physical limits of the electrical grid. Data center infrastructure simply cannot pull enough raw wattage to continuously run backpropagation on multi-billion parameter models every time business logic updates. Pushing more electricity through larger GPU clusters will not bypass this physical bottleneck. Scaling machine learning requires an architectural pivot in how AI systems store and retrieve information. Standard language models rely on implicit memory. Facts and logical rules are not stored in a discrete database. They are smeared across billions of interconnected decimal values, or parameter weights, embedded deeply within the network. Biologists refer to this as the stability-plasticity dilemma. To be effective, a network must possess enough plasticity to absorb new information, but maintain enough stability to protect its existing logic from being erased. When engineers force new, highly specific domain knowledge into these weights via fine-tuning, the values drastically shift. The model overfits to the new data, causing localized failures where broad, generalized capabilities suddenly collapse. Human neurology handles this differently. We consolidate short-term experiences into explicit long-term storage areas without physically overwriting the neural pathways that allow us to walk, breathe, or speak. In an enterprise environment, business protocols, inventory databases, and legal frameworks change daily. If an AI requires its static parameter weights to be recalculated for every compliance update, the model becomes obsolete the moment its training run finishes. Relying on implicit memory to manage dynamic, constantly updating knowledge is both mathematically unstable and economically unviable. To avoid the penalties of fine-tuning, the tech industry is expanding context windows. Models now boast limits of 1 million tokens or more, allowing users to paste entire databases directly into a single prompt. The underlying architecture of the transformer makes this approach highly inefficient. The model relies on a self-attention mechanism, meaning every single input token must be mathematically compared against all other tokens to establish context. This chart illustrates the big O notation for the self-attention mechanism, O of n squared. It plots the input sequence length on the horizontal axis against the necessary computational resources on the vertical axis. Because the scaling is quadratic, if you double the amount of text in the prompt, the required attention computation and the resulting energy load multiplies by 4. This triggers a hardware bottleneck known as the KV cache limit. Storing the massive tensor data required for million-token context windows exhausts GPU memory bandwidth long before the processors run out of raw computing power. Furthermore, dumping massive amounts of text into a prompt degrades accuracy. Models suffer from attention dilution, often called the lost-in-the-middle phenomenon, where they ignore critical data buried in the center of the text block. From an operational standpoint, AI providers bill for every token processed on every single query. Feeding an entire manual into a prompt hundreds of times a day drives operating expenses to high levels for previously processed data. Million-token context windows do not solve the memory crisis. They are a method for renting highly inefficient temporary compute that maximizes hardware strain. The viable architectural alternative is retrieval augmented generation, or RAG. This pipeline explicitly decouples data storage from the model's raw computational reasoning. Instead of feeding raw documents into the LLM, the system parses the text and converts it into semantic embeddings, translating human language into dense, multidimensional numerical arrays. A vector database stores these embeddings. It maps them within a high-dimensional spatial map, grouping the arrays based on their underlying conceptual meaning rather than relying on exact keyword matches. When a user submits a query, that prompt is also converted into a vector. The system calculates the distance between the query vector and the stored data, extracting only the nearest, most highly relevant text chunks. Only this isolated, targeted chunk of data, often just 500 tokens, is injected into the LLM's prompt. By bypassing the massive context blocks, the system avoids the O of n squared scaling trap, dropping the compute load by orders of magnitude. This removes the risk of catastrophic forgetting. Because the enterprise data lives in an external vector database, the core model never undergoes retraining, and its foundational logic weights remain untouched. Efficiency compounds further with semantic caching. If a new query mathematically matches a previous request in the vector space, the system returns the cached answer instantly, bypassing the LLM's compute cycle. In this architecture, the AI functions as a reasoning engine with an external memory bank, removing the need to store institutional knowledge inside model parameters. This external retrieval architecture is now evolving past simple search functions. Developers are beginning to treat large language models structurally like an operating system. MemGPT applies classical memory tiering to AI. The LLM's context window acts as RAM. The vector database serves as the hard drive. Through autonomous paging, the agent independently swaps data out to the database or pulls historical data back into active memory. This tiering allows AI agents to maintain coherent conversational continuity spanning months or years, while strictly operating within an optimal low-energy compute threshold. Hierarchical memory management proves that an AI can achieve infinite context scaling without suffering the quadratic energy penalties of massive context windows. While software frameworks are successfully decoupling memory from reasoning, physical hardware design is beginning to follow suit. Emerging hardware paradigms, such as neuromorphic computing processors like NVIDIA, are being designed specifically to complement this decoupled architecture. These biologically inspired chips aim to store memory dynamically at the individual artificial neuron level. This allows for local updates, bypassing the centralized backpropagation cycles that consume the majority of data center energy. Securing permits for small modular reactors or expanding grid capacity is insufficient if the underlying AI architecture remains exponentially wasteful. Scaling machine intelligence beyond current infrastructure limits requires moving away from parameter-based knowledge storage toward explicit, persistent memory structures. The long-term scalability of AI depends on the engineering of memory architectures that function within existing energy constraints, rather than relying on the continuous expansion of power generation.